Until now, we have seen how we can denoise diffusionmri data using two different methods, such as the non-local means and the local PCA and its variant, the MPPCA. Non-local means places an assumption on the signal that it is locally self-similar, or even actually non-locally self-similar, and the signal structure is repetitive, whereas the PCA-based method, that is the MPPCA, places an assumption that the signal is low rank, and we need to choose a particular rank to denoise the data. While in itself, both these approaches are really hard, as they require you to model the signal. And an alternative approach to doing the denoising is to place the assumption on the noise rather than placing it on the signal, because the signal modeling can be quite restrictive and in general is a hard problem. By placing the assumption on the noise, we can actually get better denoising performance, and this is what we will look at in this presentation. Just to give you a brief history, this observation of using statistical independence to denoise data was first made by Latin and et al. In ICML 2018. What they observed is that if you had two independent pairs of, or rather two independent measurements of the same object, then you could basically use one measurement to predict the other measurement. And what you would end up getting is a denoised version of the other measurement. This is quite an interesting property. And in ICML 2019, Joshua Batson showed that, in fact, you don't even need an image pair. You could use the same image, and you could block out a certain subset of the pixels from that particular image and still get denoising performance, which would be more or less similar to the one that you get from noise to noise. He also came up with a theoretical framework on how and why this works, which I will be talking in the next slides. Before moving to the next part, let's just quickly take a look at what self-supervised learning means. Self-supervised learning is categorized under unsupervised learning, where you don't have any labeled data. What you want to do rather is to take a part of your data, hold it out, use the rest of the data to predict the held out part. By doing so, you want to learn information about the held out part and in the process, label the data itself. For diffusionmri, what we have is basically 4D data, where you have multiple 3D volumes stacked together. Here I've represented them as G1 to Gn. It is safe to assume that noise in each volume is independent of the noise in another volume. As you can see, for example, noise in gradient direction 1 is independent of the noise in gradient direction 2, meaning that there is no correlation between the noise. The true signal, that is the brain, like whatever signal you're acquiring from the brain will actually have some correlation among the gradient directions, and that is what we want to exploit. Let's take a look at what this means in Qspace. So the data that I'm showing over here is the Stanford Hardy data set that we use very commonly across DIPY. For each of the blue spheres shown on a single shell, the B value is 2000, and I picked out randomly 3 gradient directions, 3 volumes, and actually like the middle slice for each of them. As you can see, it is possible to use one of them as a label for the other, and we will see how to do that in the next slides. Okay, before moving on, I mentioned this property of JVariance, which was introduced in Noise2Self, and I will explain on why. I'll explain what it is and how I'm going to exploit it in Patch2Self and what it means. The idea is quite simple. So let's say this is like one volume from our data, and we want to use another gradient direction as its label, right? So what we want to say is that the true signal has some correlation structure, and the noise is uncorrelated. So we are going to use Y to basically denoise X. What we hoped we had was the ground truth signal, right? So let's say the hope is that we had this ground truth signal, but we don't have any access to it. Rather, we have a noisy version. We have access to a noisy version Y of this ground truth Z. So whatever is however noise is changing in X and Y is independent of how it was mixed with Z. We assume that the noise is additive in nature. And this is where the conditional independence comes from. Like how Y is corrupted and how Z is corrupted is independent of how it was corrupting Z, right? And so we can consider Y to be a noisy label of Z. If we add that into the equation, let's say this is the objective function, which we will be training on, where f of x is one of the volumes that we want to denoise, and y is the noisy label that we have. If we just add and subtract the ground truth, which we don't have access to, and expand it out, like simply just a expansion of the square term, we would get the square of this term, like f of x minus z the whole square plus x minus y the whole square plus plus some cross product term between these two, right? And sorry, I noticed a mistake over here. This should be z, but nevertheless, it's fine. Yeah, so now that we have this expansion, I just wanted to show the ground truth being added and subtracted. Let's see. So now if we take an expectation on both sides, the expectation of this term is basically equal to expectation of both of these. And then since we know that y is independent of x given z, we can take the expectation inside. If we assume that the noise is mean zero, meaning that y y is not dependent on z, then basically we can say that expectation of y given z is equal to z, and that would make this cross product term, like this term in the cross product, equal to zero, and then this whole term can basically just go away. And what we end up with is the actual minimizing this loss, but that is the loss between the noisy data and another gradient direction that we use it as a label is equivalent to reducing the ground truth loss and the noise variance. So z minus y is nothing but the noise variance, since this is the ground truth and this is the label, right? So you're basically minimizing the noise and you are also coming closer to the ground truth. So this is our golden equation, and we'll exploit it in the Patch2Self framework. So the idea is that we will build one independent regressor to denoise each of the volumes of the 4D data, and this is how we'll do it. Since the noise in each volume is statistically independent of the noise in other volumes, but the signal exhibits some true correlation, we can build a separate regressor to denoise each of the volumes. So let's say we extract 3D patches from all the volumes in our 4D data. A patch is nothing but the 3D neighborhood, like we saw in the Machingo Pasture PCA. Then what we do is we hold out one of the volumes that is going to be the target volume that we want to denoise, and the rest of the volumes will be our training set, right? And we use the patches from the rest of the held out from the training set, that is the n-1 volumes, to predict the center of those corresponding boxes in the target set. And we do so by minimizing the self-supervised loss that I just explained in the previous slide. This is the f of x minus y, right? And this is basically minimizing the ground truth loss plus the noise variance. So let's take a deeper look at how this works. We have our gradient directions, that is our 4D data. Then we extract our patches, I call them as P neighborhoods, and we construct our regression matrix. So basically these are the n-1 volumes. So we have local patches, and we have stacked all these local patches into Casarati matrix, like we did for the PCA setting, but now we have it for all the patches for each volume. So basically, this would be 27 like if I had to take a patch radius of 1, it would be 27 of these stacked together, right? And we will just predict the center voxel of those corresponding and pad it with 0 if required. And since we are predicting only the center voxel, we will end up building a linear regression function, phi hat. Okay, we train that regression function and we get the denoised volume as output. Basically, we just feed in the same data, the one which we used to train and not the targets, just the trainings, like the training data, the n-1 volumes, we put it into the phi hat that we constructed in the training process, and you get the denoised volume. Note that the target volume is not used in the is only used as a target and is not used in the training, like the subset. Right, so now let's look at the Qspace interpretation of what's happening. So we have all these gradient directions and in this Qspace, right? What I'm basically saying is that if we hold out one of these, I can use the rest of them to predict this one. Since it is like, since the gradient directions can be visualized on a sphere, it is, you can say that I can use this and this to like some weighted combination of this and this can be shown, can be used to predict this one, and in the process we'll end up denoising. So as long as this self-supervised loss satisfies the statistical independence property, this will always work. And this is what we call J-invariant regression, or basically J-invariant functions. So the held out volume J, this is the subset dimension J, and the rest of them we use to predict it, right? And the phi that we use basically is used to denoise that particular volume. Okay, so now let's take a look at the results. So here is some simulated data. The data was simulated by basically adding Gaussian noise to the real and imaginary part to simulate like some real world noise, typically Russian in nature, and it goes from SNR5 to SNR25. So you can see that at SNR5, we do recover a tad bit better than the Marchenko posture, and at SNR10, it starts looking very similar to the ground truth. We have recovered a lot of information, and at SNR15, we are very close to the ground truth. Note that this, what we actually showed in the paper is that it is not at all sensitive to the patch size. If you have less than, let's say, 15 volumes, then you might want to play around with the patch size, but otherwise a patch radius of 0 works perfectly well. We also have comparisons against non-local means and local PCA in the paper. And then here is basically a scatter plot comparing the ground truth at different SNRs, comparing the denoised data against the ground truth at different SNRs. So at SNR10, you can see that, so if in an ideal setting with like a very good SNR, it would fall along the diagonal. And you can see as the SNR increases, that property actually shows up, and Patch2Self does better in each of these cases. Now let's also take a look at how it does on real data. So let's say, so I've shown 3 different data sets here. First is the PPMI, which is the standard 64 gradient directions DTI protocol. Then this is the Stanford Hardy. It has 150 volumes, and each at B value 2000. This one is at 1000, and this one is a multi-shell acquisition with B values up to 3500. And you can see that as the B value increases, the noise starts hampering the data a little more. And like I've also compared it against Marchenko posture PCA. As you can see, we preserve anatomical detail. We do not remove any signal structure, but we rather only suppress strictly noise components. And I think it's straightforward from the math of how J-invariance works. Just for a sanity check, I'm just showing the residuals, and the residuals do not show any anatomical structure, showing that we strictly remove only noise. Then a downstream comparison on tractography. So this is the optic radiation bundle. I have shown the comparison using the fiber to bundle coherency metric. The bluish streamlines show high coherence, meaning that they are closer to the ground truth, and the reddish yellowish ones are basically the incoherent streamlines. And you can see as you denoise your data with better denoising, the incoherent streamlines would kind of disappear. And we also compared the performance of Patch2Self on microstructure modeling. So these are the two most standard microstructure models. First is the diffusion tensor model, and the other is the constraint spherical deconvolution. In each case, so these are like two sample boxes that I picked out. So these are 150 dots. So there were 150 gradient directions in the data, and we performed a cross-validation analysis to basically understand the goodness of fit. And here is the summary. So this summary is basically showing the improvement in fitting. So for each, we have seen how much did the R-squared improve after denoising. So this is magic opacity. How much did it improve the R-squared after denoising the data? And this is how much Patch2Self improved. So as you can see, MPPCA also does give some improvement, but Patch2Self does a lot better. And these are some other examples of denoising different types of data. So for Patch2Self, we do not really have any restriction on the number of gradient directions, the type of data, the type of acquisition. It should work at any step of the pipeline, whenever you want to use it, as long as you do not start adding correlation in the noise structure across different gradient directions, you should be fine. So if you want, like, you can apply it after eddy current correction, distortion correction, susceptibility, whenever you want. And on top over here is the example of cardiac MRI. This is a porcine ex vivo data acquired by Dr. Daniel Ennis's lab. This is a spinal cord T1 weighted image. So this is an interesting one. Here, it is not a diffusion acquisition, but we had multiple repetitions of the spinal cord data. And just applying Patch2Self got rid of the uncorrelated noise components, just how you would expect it. And now let's take a look at how Patch2Self is implemented in DIPY. Right, now let's take a look at how Patch2Self is implemented in DIPY. To use Patch2Self via DIPY, all you need to do is import it like this. So it is within the denoise submodule. You just need to import Patch2Self. Then you load your Nifty file and your bval file. Patch2Self requires the bval file as input because we denoise the B0s and the DWI volumes separately. So it is done automatically. You don't really have to do anything. And as for the parameters, there are two important, I would say one important parameter, that is the model. So if you have, like, I would generally set this model to OLS, but most of the times Reg and OLS give me similar performance, but it's highly dependent on your data set. Also, as you can see, there are two more parameters, the shift intensity parameter and the clip negative values parameter. What these two do is basically in shift intensity, I shift the negative values back to back on a positive range while preserving the variance. And in the clip negative values, basically all negative values are clipped to 0. Depending on your data set, you might want to play around with these. Only one of them should be true. By default, the clip negative values is true, but it's again data set dependent. I have not tested all the data sets in the world, but sure, like one of these two is definitely going to work for you. Here I have the PPMI dataset, which I used in the MPPCA example. As you can see, it finishes quite quickly. It took 131 seconds. And this is the denoising output. So let's look closely. As you can see, it has suppressed quite a bit of noise, preserved all the structural details. You do not see any anatomical structure in the residuals, which is a good thing, meaning that we haven't gotten rid of any uh, signal, the anatomical signal, which is great. And here is the output from the OLS. It should look more or less similar. The noise pattern is also very similar, meaning that it really did not make a difference choosing OLS and Ridge. And here is an example with the spinal cord data. For spinal cord, basically, it took literally 2.5 seconds, 2.4 seconds, super fast. The size of spinal cord data is generally very small. And you can see it suppresses quite a bit of noise, preserving the structure, and also the residuals are random, meaning that we don't remove any structure in the data. So to use the command line, all you need to do is call this command, DIPY denoise Patch2Self, and pass the DWI file along with the bval file. The DWI file is DWI underscore CORR, and the bval file is the CORR, and I've set the verbose flag. So basically you can see the output being printed out over here. You can also see that it is by default saved in the file name DWI underscore patch2self.ini.gz. You can change the file name by using the outdenoised option. To look at all the options in the command line, all you need to do is to the -h option is basically the help, and it should show you all the options along with the citation and what the parameters mean. So as you can see, you can set the output directory, you can set the output, so outdenize stands for the output file name, and these are the default input, like these are required. So the input file is the DWI file and the bval file.